Jnanam paramam dheyam. Knowledge is supreme.
Okay, so we have this one. Now let us go back to the what we want to define. So now here you have a lot of things to be checked, but as I said, you can take this TFR pamphlet. It has all the definitions and this. Okay, so now I want to define two things. So for a ring, I want to define what is called a global dimension. Of it, and then after we have done this, then we will have its what is its relation with the Krull dimension. So that will come later, but how do you, for the definition of global dimension, all modules are involved. So this global dimension is usually denoted by GL dim A. This is by definition supremum of homological dimensions of M over A. So the supremum is running over all modules, M is A module. So you see it's very big to understand this. Even to say it is finite contains lot of information about the ring. So what we will prove the theorem, what we want to prove is, if the global dimension is finite, that is equivalent to saying the ring is regular, and in that case global dimension equal to Krull dimension. Okay, so this is what will come in the few lectures ahead. So we have to define what is the homological dimension. So homological dimension. So first of all, suppose given a module M and we have this projective resolution of M. Projective resolution. We will say this projective resolution has length n if after nth term all the terms are 0. So that means, so this has P has length n, means Pn is non-zero and later ones are 0, and Pi's are 0 for all I bigger than n. So that simply means there is a projective resolution of this type, M0, P0, Pn and then 0, and this is definitely non-zero. If it is 0, then we will not write that. No. So it's, so this means it's a length, this n is called a length of the projective resolution. So now homological dimension of the module is by definition the least n such that there exists a projective resolution P dot M of length n. If it does not exist, if there is no such integer, then you denote it to be infinite. So otherwise infinity. That means all, in that case all projective resolutions will have, no, it will not, none of them will be finite. So such a thing is called the homological. So this integer n is called the homological dimension. The homological dimension of a module can be infinite or finite, but if the module is 0, then we put homological dimension of the module to be -1. So for example, when is the homological dimension 0? homological dimension is 0 if and only if, what does our definition say? That means this least integer is 0. That means there is only one term, there is a projective resolution is only one term. So, that means this is if and only if P0 to M, this is a projective resolution, this term is 0, but that means this is an isomorphism. So, that means this M is projective. So, in some sense this homological dimension measures, it is a measure how far is the given module from a projective module. So, if the homological dimension is 0, that means the module is projective. So, in particular homological dimension of a free module is 0. Okay. Now, let us make some remarks or some basic properties about the homological dimension. How does one calculate and what is its this for 0 homological dimension, it is a nice description, but otherwise we will have to work with the module x. So, for example, this proposition. So, M is a module. So, many things here may work out without assuming the ring is Noetherian or modules are finitely generated. But I suggest when one learns first time, one assumes, you usually assume the ring is nice, Noetherian and modules are finitely generated, because in the first time itself the difficulties. So, one will not know where is what thing is important and where is why the conditions are put like that. So, the following are equivalent for a module, the following are equivalent. So, one, I am just recording this the earlier homological dimension 0 case, and then we will generalize. M is projective. Two, see there is only one term. So, therefore, if I take this projective resolution definitely, and if I take the if I apply home and compute the homologies, then all other terms are 0, therefore, there won't be any contribution from kernel and image. So, that simply mean that x j m comma n equal to 0 for all A modules n and all indices j bigger equal to 1. 3 x 1 m comma n is 0 for all A modules n. So, proof, see condition 3 is better because you only have to check only one condition x 1. So, first of all 1 implies 2 is because if M is projective, then I could simply take this as a projective resolution. This is my P naught and this is my ID map. So, this will be projective resolution, and to compute this x, I will apply home functor home dash m to n to this exact sequence and compute the x, and whatever comes after that there will be 0, that is why this condition 2. And 2 implies 3 is obvious. Now, the real implication one needs to prove is 3 implies 1. So, if x 1 m n is 0 for all modules n, then I want to prove m is projective, that is the real. So, this implication is the real implication. So, let us prove this. So, I want to prove the module M is projective. That means what? That means the definition was what? If I have n and n double prime two modules and a surjective map and given a map from M to this phi and f, then I am looking for a lifting like this f bar, so that this diagram is counted. That is what, that is how one proves the module is projective. Okay, but once we are given a surjective map like that, then I can write a kernel here and then we get an exact sequence. Once I have exact sequence like that, short exact sequence like that, and when I apply the functor home a m dash, if I apply this, so let us call this as n prime, then what do I get? Home is left exact. So, I will get, so home a, oh, it is a contravariant, no, it is a covariant. So, this home m n prime home a n, oh, let us, I have changed, no, correct, m n and then home a m and double prime and to 0 is, this is the home is left exact. And what will be the next term? So, they will be connecting homomorphism here and the next term will be x1 m comma, it starts here again n prime and x1 m n and so on. And what is that we want to prove? We want to prove that this is, we have given this is 0, this is 0 is, that is what we have given in 3, because x1 mn is 0 for all modules, in particular first. So, this is 0, but this 0 means precisely this map is surjective, but that precisely means the functor home m is exact, and that was one of the equivalent condition for a module M to be projective. So, that proves one. Okay, so write it. So, that is how one usually deals with this, the usual calculation with the X modules will be done by diagram chasing and writing a big long exact sequence of X modules which are connected to each other by connecting homomorphisms. Okay, so you can now, so this is like homological dimension 0. This means homological dimension of M is 0. Now we will state an analog of this proposition where homological dimension is bigger. So that one is proposition so M is an A module, then the following are equivalent. So the first condition will be homological dimension of M is less equal to N. So this means, what does this mean? This means there is a projective resolution of M whose length is at most 10, because the last nth term may be 0, may not be 0. If it is 0, it will be still smaller and so on. So this second, x j mn is 0 for all A modules n and indices j bigger equal to n plus 1. Third, x n plus 1 m comma n is 0 for all a modules n. So, this n and this. So, you have to compute x n plus 1 and test whether it is 0 or not 0. If it is 0, homological dimension is less equal to n. Okay. Fourth condition is, this is a restatement. So, but it is useful to state it. So, given m, so there if m to p0 pn minus 1 to kn to 0. If this exact sequence of a modules with p0 up to pn minus 1 are projective modules, and kn is the kernel. No, so when you start resolving m, you start writing a quotient of a projective module and then take the kernel and do that, repeat the process, and you stop it here. This is only the kernel here. Now, the next step will be resolve this also. That means, write this kn as a quotient of a projective module and club it here. But if you stop there, then then kn is already projective. That is the condition 4. So, when you try to write a projective resolution, 4 says, when you try to write a projective resolution for m, keep doing this, at nth stage you already get a projective module, and that is where that is equivalent to homological dimension is less equal to n. And the proof of this is same like earlier. Now, you have to take this definition and apply home mn and then take the long exact sequence and do that thing. So, that I will not prove this. So, proof see TFR pamphlet. Okay, so as a immediate corollary, you can write it homological dimension of the module M is a supremum over N, where there exists an A module N with X N A M N is non-zero. The largest n, so that for some module n, this x10 m is non-zero. That is the homological dimension of M then. Because you see here, this proposition says homological dimension less equal to n is saying equivalent to saying that x10 plus 1 is 0. So, if it is equality here, this is 0, but earlier should not be 0. So, that is x10 mn should not be 0. Alright, another corollary I want to write it for future use. Another corollary is, suppose you have a module M is A module and N prime is a submodule, M prime is a submodule, A submodule. If M prime is a direct summand of M, then homological dimension of m prime is less equal to homological dimension of m. Homological dimension will not be more than the original module if it is a direct summand. So, proof. So, I will use the earlier corollary. If I want to prove this homological dimension is smaller or equal to this. So, first of all, let us call this homological dimension to be n. Then what do we know? We know that x n, there is a module n, so that this x n m and this is non-zero for some a module n. This is by earlier corollary. Well, okay. Now, when this is a direct summand, that means what? That means we have m prime here, m here, and this means that this m is m prime direct sum m double prime. So, you can take the projection here and then this. That means this short exact sequence is split. So, this is a split short exact sequence. And when you have a short exact sequence which is split, then it will when you apply home, it will remain split. So, it will remain exact. So, therefore, as a result, this if I compute by using this and the long exact sequence, then x n m prime n prime is a direct summand of x n m n. This is non-zero. So, this it is a direct summand here. So, it may be 0, it may not be 0, and this is true for. So, therefore, a smaller equal to. So, the submodules of a module will not have more homological dimension. Okay. So, now, another observation I will need is, let us write it as a proposition. This is when we want to compute the homological dimension. So, the earlier corollary says homological dimension of a submodule will be finite and it will not be more than the original module if the homological dimension of the original module is finite. So, this is similar. So, proposition. So, suppose we have a short exact sequence like this, m prime to p to m double prime to 0, and where with p projective. You will arrive such short exact sequence typically when you try to resolve some module and break the big resolution into short pieces, because what will you do then? You will take the image and kernel. So, this will be the image and that will be the kernel. So, this will be a typical situation there. So, then when is this projective and when is this projective? That is what our concern is, and what are the homological dimensions, right. So, then one says if m double prime is projective, then this is also projective, then m prime is also projective. Two, if homological dimension of, so this this is like this one is very special case. So, you should read like this: M double prime projective means homological dimension is 0. This homological dimension is also 0 because of its projective. So, then this is projective, then this homological dimension is also 0. Now, the second statement I am writing is, if this homological dimension is something, then what is the relation between the homological dimension of this and this. So, if homological dimension of M double prime is bigger equal to 1, then homological dimension of M double prime, then what it is? This one is homological dimension of M prime plus 1, and it may happen that both these are infinite size, it may happen both sides are infinite. In that case there is nothing to prove. So, okay, so let us prove it, that will reveal. Okay, so first of all, the one is clear because you have this exact sequence and we are assuming this is projective. If this is projective, then it will be a split exact sequence. That means this M double prime is a direct summand of P, but direct summand of a projective module is also projective, and a direct summand, but what will be the other complement will be this M prime. Therefore, one is clear. So, one is clear since direct summand of a projective is projective. Is projective. Okay, 2. Okay. So, when I try to compute now the x from this sequence, see what we have to do is we have to compute the x to decide what is the homological dimension. So, when I apply, so you take the projective resolutions of this, each one of them, apply home to home dash n to that, and then compute the homologies, and then we will get exact sequences of complexes, and then we will have to use that connecting homomorphisms. But then see, in the middle module is projective, so I will take the special projective resolution for that, namely only one term projective resolution and all these. So, in that case, for I will write the result for an A module n and any integer n, what will we get? We get x n m prime n and then x n plus 1 m double prime n. See, this will be connective homomorphism. See, before that these things will come, but that will be 0, and after that also it will be 0, because then I will put 0 here and put 0 here. So, the putting 0 here means these modules are isomorphic, but once these modules are isomorphic, so since here we have used the fact that since P is projective. So, if this is 0 at some stage, then that will be 0, but that will mean this formula. If this is 0, then this is 0. So, that means the homological dimension of M double prime will be exactly one more than that. So, that proves the thing.